Hello there, and welcome to this exploration, where the familiar becomes strange, where a single moment, low-salute million years ago, changed the course of life on Earth forever, and where the end of one world became the beginning of another. Tonight, we're not looking at distant galaxies or diving into ocean depths. We're traveling back through deep time to witness the most famous extinction event in Earth's history, the day the dinosaurs died. This is the story of the asteroid impact that ended the Mesozoic era, not the dinosaurs as movie monsters or children's cartoon characters, though they've become both in our culture. Not the asteroid as just another space rock, though it was traveling at unimaginable speeds, but the complete story, the geology, the physics, the chemistry, the biology of what happens when a mountain-sized piece of rock and metal slams into a living planet at kilometers per second. And before we begin this journey into catastrophe and survival, into fire and darkness and eventual rebirth, I'd love to know, have you ever looked up at the night sky and wondered what's out there? What might be heading our way, because the universe is not empty, not safe, not concerned with our survival. It's filled with debris from the solar system's formation, rocks and ice and metal hurtling through the darkness, and occasionally, inevitably, those objects intersect with Earth's orbit. Now, if this kind of exploration speaks to you, if you've ever wondered how we know what we know about ancient catastrophes, how scientists can read the story of a single day, low-salute million years ago written in rock and ash and shocked minerals, I'd be grateful if you tapped like or subscribed. It helps this signal reach others who look at the present and wonder about the deep past, who understand that what happened then matters now, that the planet has a memory and we're learning to read it. And so settle in, feel the solid ground beneath you, because we're about to witness its violent disruption. We're going to watch as the Cretaceous world, thriving and diverse and utterly unprepared, faces an extinction event so catastrophic that it erased 500 Chisarwur of all species on Earth. We're going to stand at ground zero, feel the shockwave, experience the darkness that followed, and understand how life, against all odds, found a way to survive and eventually flourish in the aftermath. And the asteroid has a name now, Chicxulub, after the town in Mexico's Yucatan Peninsula, where the crater it created was finally discovered in the Ichenjubai. The dinosaurs had ruled for Ibite Losher million years, and in a single day, a single moment of cosmic violence, their reign ended. The clock is ticking. The asteroid is approaching, and Earth has no idea what's about to happen. Let's begin to understand what was lost. We first need to understand what existed. The late Cretaceous world, approximately low-salute million years ago, was Earth, but not Earth as we know it. The continents were in different positions, the climate was warmer, sea levels were higher, and life had evolved forms that would seem alien to us if we could somehow visit. Let's start with the geography. The supercontinent Pangaea, which had existed during the early Mesozoic, had long since fragmented. The Atlantic Ocean was opening, pushing North America and Europe apart at a rate of a few centimeters per year, slow by human standards, but rapid in geological time. South America and Africa, once joined, had separated, creating the South Atlantic. India, which had broken away from Madagascar and Africa, was racing northward across the Tethys Sea toward its eventual collision with Asia, an impact that would one day create the Himalayas. But that collision was still tens of millions of years away. In the late Cretaceous, India was an island continent, isolated, developing its own unique fauna. Australia and Antarctica were still connected, forming a single landmass far to the south. The geography was transitional, caught between the ancient configuration of Pangaea and the modern arrangement of continents we recognize today. The climate was much warmer than today. There were no ice caps at the poles. Forests grew in Antarctica. Crocodilians swam in Arctic rivers. The temperature gradient between equator and poles was less extreme than now, meaning less vigorous atmospheric circulation, different weather patterns, different seasonal variations. Sea levels were about meters higher than today, flooding vast areas of the continents, creating shallow inland seas. In North America, the Western Interior Seaway split the continent from north to south, connecting the Arctic Ocean to the Gulf of Mexico. This shallow sea, hundreds of kilometers wide in places, teemed with marine life, mosasaurs, this giant marine reptiles that could reach starward meters in length, plesiosaurs with long necks and paddle-like flippers, enormous sea turtles, countless species of fish, ammonites, and belemnites. The seaway would play a crucial role in the story of the extinction, but we'll return to that. The vegetation was different too. Flowering plants, angiosperms, which had evolved during the Cretaceous, were diversifying rapidly, transforming terrestrial ecosystems. Before the Cretaceous, land plants were dominated by ferns, cycads, and conifers. But by the late Cretaceous, flowering plants had become common, creating new ecological niches, new food sources, driving coevolution with insects, particularly bees and butterflies, which were also diversifying. These flowering plants created more complex forest structures, with understory vegetation, with seasonal flowering and fruiting, with chemical defenses against herbivores. They changed the rules of terrestrial ecology, providing new opportunities for herbivores that could digest them, for insects that could pollinate them, for predators that could exploit the new habitats they created. And then there were the dinosaurs. They had dominated terrestrial ecosystems for over million years by this point. And they had evolved into an astonishing diversity of forms, from the massive long-necked sauropods like Alamosaurus, which could weigh cirstans and reach lengths of centimeters, to tiny feathered dinosaurs barely larger than chickens. They occupied every terrestrial niche, herbivores small and large, carnivores ranging from human-sized hunters to apex predators like Tyrannosaurus rex, omnivores, insectivores, specialized forms adapted to countless different environments. The image of dinosaurs as slow, cold-blooded, unintelligent reptiles is outdated. Modern paleontology, informed by decades of new discoveries, biomechanical analyses, and studies of bone microstructure, paints a very different picture. Many dinosaurs were likely warm-blooded, or at least able to maintain elevated body temperatures through metabolic heat production. Many were covered in feathers, not scales. Feathers that provided insulation, enabled display behaviors, and in some lineages, eventually enabled flight. Dinosaurs built nests, cared for their young, lived in social groups. Some species show evidence of complex behaviors, cooperative hunting in some theropods, herding in many herbivores, elaborate display structures like the crests of hadrosaurs, which may have been used for acoustic communication. They were successful, diverse, thriving. Tyrannosaurus rex, perhaps the most famous dinosaur, lived during the very end of the Cretaceous in what is now western North America. It was the apex predator of its ecosystem, reaching lengths of meters and weights of bat tons or more. Its bite force was the strongest of any terrestrial animal that has ever lived, capable of crushing bone. Its teeth were not knife-like but thick and robust, designed for gripping and tearing, for delivering devastating bites that would incapacitate large prey through massive tissue damage and blood loss. And Triceratops, a common herbivore in the same ecosystems, was built like a living tank, a massive skull with a bony frill and 3 horns, a powerful beak for cropping vegetation, batteries of teeth for processing tough plant material. Adults could weigh lotfu tons. They likely lived in herds, providing some protection from predators through numbers and collective defense. Cute hadrosaurs, the duck-billed dinosaurs, were among the most successful herbivores of the late Cretaceous. They had hundreds of tightly packed teeth forming grinding surfaces that could process even tough plant material. Many species had elaborate crests on their heads, hollow structures connected to the nasal passages that may have functioned as resonating chambers, allowing different species or even individuals to produce distinctive calls. And then there were the flying reptiles, the pterosaurs. These were not dinosaurs, but a separate lineage of archosaurs that had evolved powered flight. By the late Cretaceous, some pterosaurs had reached enormous sizes. Quetzalcoatlus, discovered in Texas, had a wingspan of surfushirimeters, making it one of the largest flying animals ever to exist. It was probably a terrestrial stalker when not flying, using its long neck and sharp beak to hunt small animals on the ground. The oceans were dominated by marine reptiles that had returned to the sea from terrestrial ancestors. Mosaurs, which evolved from monitor lizard ancestors, were the apex predators of many marine ecosystems, filling the niche that sharks and orcas fill today. They had powerful jaws, flexible skulls that allowed them to swallow large prey, streamlined bodies, and paddle-like limbs. Plesiosaurs, with their characteristic long necks and 4 flippers, hunted fish in the open ocean and in shallow seas. Some species had necks containing tierced or more vertebrae, giving them incredible reach to snatch fish. And then there were the ammonites, externally shelled cephalopods related to modern nautilus, squid, and octopus. They had existed since the Devonian, over 7 million years ago, surviving multiple extinction events, diversifying into thousands of species, with shells ranging from a few centimeters to over meters in diameter. They were among the most successful marine invertebrates, filling countless ecological roles. This was the world of the late Cretaceous. Warm, biodiverse, dominated by lineages that had ruled for tens of millions of years. They were mammals, yes, but they were small, mostly nocturnal, occupying niches in the undergrowth, in burrows, in the trees. They were birds, descendants of theropod dinosaurs that had evolved flight, but they were not yet dominant. The world belonged to reptiles, on land, in the air, in the sea, and this world was about to end, not gradually, not through slow climate change or competition with new species or volcanic eruptions, though volcanoes would play a supporting role in the story. But suddenly, catastrophically, in a single day of violence that would reshape the entire planet. Because while life flourished on Earth, something was approaching from space. An asteroid, a remnant from the formation of the solar system 4.6 billion years ago, had been orbiting the Sun for eons, occasionally perturbed by the gravitational influence of Jupiter, by close approaches to other asteroids, slowly evolving its orbit, and through chance, through the random mechanics of celestial motion, that orbit was about to intersect with Earth's. The dinosaurs, with all their evolutionary success, with all their adaptations, with all their diversity, had no way to see it coming, no way to prepare, no way to survive what was about to happen. The asteroid was roughly 10 to 15 kilometers in diameter. For scale, that's about the size of Mount Everest, or the distance from downtown Manhattan to the northern Bronx. It was composed of rock and metal, carbonaceous chondrite material, similar to the most primitive meteorites we find today, material that had never been processed through a planet's interior, that had remained largely unchanged since the solar system's formation. It had mass,
Estimates suggest 1 to 4 times 10^15 kilograms. To put that in perspective, that's about 1 trillion metric tons, the weight of hundreds of billions of elephants, the combined weight of all humans who have ever lived multiplied by thousands. And it was moving fast. As it entered Earth's gravitational influence, its velocity increased. By the time it hit the atmosphere, it was travelling at approximately 20 kilometers per second, or about 72,000 kilometers per hour. At that speed, you could cross the United States in less than a minute. The kinetic energy of motion, carried by the asteroid was approximately 100 million megatons of TNT equivalent. That's roughly 2 million times more powerful than the largest nuclear weapon ever detonated. It's more energy than all the nuclear weapons in existence today, detonated simultaneously, multiplied by hundreds. This was not a rock falling from space. This was a cosmic bullet, a planet killer, travelling at a velocity that compressed the air in front of it until it became plasma that would strike the Earth's crust with such force that rock would behave like fluid, that would inject so much energy into the planet's surface that the effects would be global, immediate, and catastrophic. Where would it hit? Through the random chance of orbital mechanics, through the timing of Earth's rotation, through pure bad luck for the organisms living below. The asteroid's trajectory brought it to a specific point on Earth's surface.
The Yucatan Peninsula in what is now Mexico. A shallow tropical sea, warm and clear, teeming with marine life. Reefs grew in the shallows. Fish darted between coral formations. Ammonites drifted in the water column. Marine reptiles hunted. On the nearby shores, dinosaurs grazed. Theropods stalked. Pterosaurs soared on the ocean breeze. It was a normal day. The sun rose. Animals fed. Predators hunted. Life continued its ancient rhythms, completely unaware that in moments everything would change. Let's slow down time. Let's examine what happened, second by second, as the asteroid entered Earth's atmosphere and struck the surface. T- seconds, atmospheric entry, the asteroid hits Earth's upper atmosphere, traveling at kilometers per second. At this velocity, air molecules don't have time to move out of the way. They compress in front of the asteroid, and that compression generates enormous heat, temperatures reaching tens of thousands of degrees Celsius. The asteroid itself begins to heat. Its surface starts to vaporize, creating a brilliant fireball visible from thousands of kilometers away. To any organism that happened to be looking up at that moment, the asteroid would appear as a new sun, brighter than anything they had ever seen, growing larger with terrifying speed. The sonic boom is beyond comprehension. The shock wave from the asteroid's passage through the atmosphere travels outward at supersonic speeds, shattering anything fragile, creating a roar that dwarfs any thunder, any volcano, any sound that has ever existed on Earth. T-U seconds, the asteroid has passed through the stratosphere, through the troposphere, is approaching the surface. It's still traveling at approximately 8 kilometers per second. The air compressed in front of it has become a plasma fireball, radiating intense heat downward. Animals on the ground, if any are still alive after the atmospheric shockwave, are being incinerated by radiant heat. The ocean surface is boiling, vegetation is igniting, the sky has turned white with superheated plasma. T-E second, the asteroid is about to impact. It will strike at a slight angle, approximately Lichter's degrees from horizontal. Not a straight vertical impact, but angled enough that much of its energy will couple into the crust, rather than simply excavating straight down. This angle, determined by analysis of the crater structure, would prove particularly devastating for spreading ejecta globally. And the impact point is in shallow water, perhaps, ebat fu Urbeck meters deep, covering limestone and anhydrite calcium sulfate bedrock formed from ancient reef systems and evaporating seas millions of years earlier. At T-Ling impact, the asteroid strikes. In the first microseconds, the physics is almost incomprehensible. The asteroid is still traveling at kilometers per second when it makes contact. The rock at the impact point doesn't have time to move out of the way. Instead, it experiences pressures measured in millions of atmospheres, temperatures measured in tens of thousands of degrees. The asteroid begins to vaporize on contact. The target rock also vaporizes. A massive shock wave propagates outward from the impact point at hypersonic velocities, moving through rock faster than sound moves through air. The kinetic energy of ebat million megatons begins to transfer into the crust. The ground does not simply crack or shatter. Under such extreme pressures and temperatures, solid rock behaves like a fluid. It splashes, it flows, it rebounds. Second, the asteroid has completely penetrated the shallow ocean and has plowed into the bedrock. It's vaporizing as it goes, transferring its momentum and energy into the crust. A crater is forming, but not through simple excavation. The rock is being compressed, melted, vaporized, and thrown outward at velocities that reach escape velocity. Kenk. A massive plume of vaporized rock, seawater, and asteroid material is already rising into the atmosphere. This plume is moving upward at several kilometers per second, glowing white-hot, carrying material that will eventually spread across the entire planet. The shock wave is propagating outward through the bedrock. Within seconds, it will trigger earthquakes across the entire Caribbean region. The magnitude of these earthquakes will dwarf anything in human experience. Estimates suggest magnitude, third or higher on the Richter scale, though the scale becomes somewhat meaningless at such extremes. Seconds, the crater is rapidly expanding. Material is being excavated outward and upward. The initial cavity is reaching depths of kilometers into the crust, far deeper than the ocean, cutting through sedimentary rocks into the crystalline basement beneath. The excavated material is being thrown outward in sheets and curtains. Some of this material, the closest to the impact, is moving so fast it will leave Earth's atmosphere entirely. Some will fall back, some will orbit before re-entering. Some may escape Earth entirely. The impact has created a shock wave in the atmosphere, as well as the ground. This atmospheric shock wave is propagating outward at supersonic speeds, creating a blast wave that will circle the globe multiple times before dissipating. The water of the shallow sea has been completely vaporized within hundreds of kilometers of the impact. What was ocean is now superheated steam and plasma. This water will eventually return as torrential rain, but not yet. For now, it's part of the expanding fireball. The crater has reached its maximum depth and is beginning its modification phase. In a large impact, the crater doesn't simply remain as a deep hole. The rock beneath, released from the enormous pressures, begins to rebound. Material flows back toward the center, creating complex structures. The central peak begins to form, a mountain of rock pushed upward by the elastic rebound of the crust, rising kilometers above the pre-impact surface before collapsing back down to form a central peak ring. This process happens in minutes, with solid rock flowing like water under the extreme conditions. Meanwhile, ejecta is falling back to Earth across vast areas. Material thrown straight up is starting to re-enter the atmosphere at hypersonic speeds. Like the asteroid itself, this material is compressing the air in front of it, heating it to incandescence. The sky is beginning to glow, not from sunlight, but from returning ejecta. Thousands, millions, billions of particles, ranging from dust-sized to house-sized, are re-entering the atmosphere simultaneously across the entire hemisphere. The radiative heat from this re-entering material is intense, measured in watts per square centimeter, comparable to an oven broiler. On the ground, anything flammable is beginning to ignite. Forests, underbrush, dead vegetation, all are catching fire. The global firestorm is beginning. T-tot sur minutes, the crater has reached its final configuration. It's approximately Ebet Basher's Fu Urbet kilometers in diameter, one of the largest impact craters in Earth's history, and certainly the youngest large crater. The structure includes a peak ring about Basher's kilometers in diameter, surrounded by a deeper trough, surrounded by an outer rim of fractured and uplifted rock. The depth is moderated from the initial sensors kilometers to about 8 kilometers deep in the central basin, still far deeper than anything we experience in the modern world. The Grand Canyon, for comparison, is less than 8 kilometers deep. The floor of the crater is molten rock, impact melt generated by the shock of the collision. This melt will eventually cool and solidify, creating a layer of glassy material that will preserve the evidence of the impact for millions of years. But beyond the crater, devastation is spreading globally. The atmospheric shockwave has traveled thousands of kilometers, flattening forests, creating hurricane-force winds, stripping vegetation from the ground. Animals hundreds of kilometers from the impact are being killed by the blast wave, by flying debris, by the sheer violence of the air itself moving at supersonic speeds. And the ejecta continues to fall. The heating of the atmosphere by re-entering material has created what some scientists call the heat pulse, a period of perhaps sensors minutes to an hour where the sky itself becomes an infrared oven. Surface temperatures across much of the planet spike to several hundred degrees Celsius. Any organism exposed to the open sky during this heat pulse is going to be cooked. Smaller animals can shelter in burrows, underwater, in caves, beneath rocks. But large animals, particularly large terrestrial animals like dinosaurs, have nowhere to hide. Their mass makes them vulnerable. They can't fit in burrows, can't submerge completely, can't escape the radiative heat. Now, the global wildfires are intensifying. Forests across North America, South America, possibly other continents are burning. The smoke from these fires is beginning to rise into the upper atmosphere, joining the dust and sulfur from the impact itself. Dem-dut-e-hour, the immediate effects of the impact are stabilizing. The crater has formed and cooled slightly. The ejecta has largely finished falling, though fine material will continue to drift down for days or weeks. The atmospheric shock wave has propagated around the entire planet, though it's weakening as it spreads. But the secondary effects are just beginning. The heat pulse has triggered massive wildfires on multiple continents. The smoke from these fires is darkening the sky. And something else is happening, something that will prove critical to the extinction event. The impact occurred in rocks rich in sulfur compounds and hydrite beds formed from ancient evaporated seas. The impact vaporized these rocks, injecting an estimated Ebet-Fu-Ubet gigatons of sulfur into the atmosphere in the form of sulfur dioxide. When sulfur dioxide reacts with water vapor in the atmosphere, it forms sulfuric acid aerosols, tiny droplets that remain suspended in the air. Relaxations to 4. These aerosols are extremely effective at reflecting sunlight back into space. They also don't rain out quickly. They can remain in the stratosphere for years. Combined with the dust from the pulverized rock, with the soot from the global wildfires, with ash from volcanic eruptions that were probably triggered by the seismic shock of the impact, the atmosphere is filling with particulates that will block sunlight for months or even years. The temperature is beginning to drop, not everywhere immediately, close to the fires, it's still unbearably hot. But the global average temperature will fall dramatically. Some climate models suggest a drop of Serfu degrees Celsius within weeks, with even greater drops in some regions. And this is where the true extinction begins. Not from the immediate violence of the impact, though that killed everything within thousands of kilometers, but from the environmental collapse that follows. The asteroid impact was not a single catastrophe, but a cascade of interconnected disasters, each feeding into the next, each amplifying the others. Let's examine the killing mechanisms one by one, understanding how they operated, what species they affected, why some organisms survived while others perished. The initial blast, everything within perhaps ubat kilometers of the impact point died instantly. The combination of the atmospheric shock wave, seismic shaking, radiant heat, and ejected material was simply unsurvivable. The rock itself was pulverized, the ocean was vaporized. Any organism unlucky enough to be in this region ceased to exist in any recognizable form. This immediate kill zone, while devastating, represents a relatively small fraction of Earth's surface, perhaps 1/4 of the total. Most species existed beyond this range. The impact itself was not enough to cause a mass extinction. It was what followed that mattered. The heat pulse, as discussed earlier, the re-entry of ejecta heated the atmosphere globally for perhaps an hour. This heat pulse would have been particularly intense in regions with a direct view of the sky, where ejecta was re-entering essentially the hemisphere facing the impact, and to some extent the opposite hemisphere, as material fell from orbit. Small animals could shelter. Organisms in water deeper than a meter or so would be protected. Water is an excellent heat shield. Organisms in burrows, in caves, under rocks, even in dense forest where the canopy might provide some protection, had a chance. But large terrestrial animals, particularly those in open environments, were exposed. And the evidence suggests that non-avian dinosaurs, especially large species, did not survive this heat pulse in any significant numbers. The selectivity of the extinction supports this mechanism. Large terrestrial animals suffered catastrophic losses. Small terrestrial animals, particularly those with burrowing habits, survived in much greater numbers. Freshwater organisms had higher survival rates than terrestrial ones. Marine organisms in deep water survived better than those in shallow coastal environments. Global wildfires. The heat pulse ignited vegetation across vast areas. The fossil record shows a layer of soot globally distributed at the Cretaceous-Paleogene boundary, often called the KPG boundary or KT boundary in older literature. This soot comes from burning vegetation, wood, leaves, undergrowth. The extent of these fires is debated. Some scientists think the entire planet's forests burned. Others suggest a more patchy distribution, with fires in some regions but not others, depending on factors like humidity, recent rainfall, vegetation type. Either way, the fires consumed enormous amounts of biomass, injecting soot and smoke into the atmosphere, adding to the darkening caused by impact dust and sulfur aerosols. They also destroyed habitat, removed food sources, and created a landscape of ash and devastation. For herbivores that survived the initial impact and heat pulse, the loss of vegetation was catastrophic. For carnivores that depended on those herbivores, the effects cascaded up the food chain. Large animals with high metabolic requirements were particularly vulnerable. See impact winter. This is perhaps the most devastating effect, the one that turned a regional disaster into a global catastrophe. The combination of dust, sulfur aerosols, and soot created an atmospheric shroud that blocked sunlight for months, or possibly years. Sunlight is the energy source for nearly all life on Earth's surface. Photosynthesis by plants and phytoplankton marine microalgae converts solar energy into chemical energy stored in organic compounds. These primary producers form the base of food webs. Everything else, with rare exceptions like deep-sea chemosynthetic communities, ultimately depends on photosynthesis. When sunlight is blocked, photosynthesis stops. Plants stop growing. Many plants die, particularly annuals and species without energy reserves to survive prolonged darkness. Phytoplankton populations crash. The entire base of the food web collapses. Climate models of the impact winter suggest that light levels dropped to less than Bifrene of normal, too dark for most photosynthesis. Temperatures plummeted. Estimates vary, but a drop of Surfu degrees Celsius in global average temperature is commonly cited, with even greater drops in continental. This cold would have been particularly devastating for large reptiles, if any had survived the earlier phases. Unlike mammals and birds, which can maintain body temperature metabolically, reptiles depend on external heat sources. In prolonged cold, they become sluggish, unable to feed effectively, vulnerable to starvation. The darkness lasted months at minimum. Some estimates suggest photosynthesis would have been suppressed for Sen years. During this time, ecosystems dependent on primary production would have collapsed. Food chains longer than a few links became unsustainable. Large carnivores at the top of the food chain, requiring enormous amounts of prey to sustain themselves, would have starved as prey populations declined. Large herbivores, requiring vast amounts of vegetation, would have found less and less to eat as plants died and weren't replaced. Small animals with low metabolic requirements, omnivores that could eat a variety of foods, including detritus, scavengers that could feed on the dead biomass from the extinction event itself, these had advantages. Ocean acidification. The immediate aftermath of the impact saw ocean acidification on a scale rarely experienced in Earth's history. Multiple mechanisms contribute. The vaporization of limestone calcium carbonate in the target rocks released massive amounts of CO2 into the atmosphere. Some estimates suggest cbyte gigatons of carbon were injected within hours. Second, the global wildfires released additional CO2 from burning vegetation and organic matter in soils. This CO2 dissolved into the ocean, forming carbonic acid, lowering pH. The ocean surface became more acidic within years to decades. Ocean acidification affects organisms that build shells or skeletons from calcium carbonate. In more acidic water, calcium carbonate is less stable, harder to precipitate, more prone to dissolution. Organisms must expend more energy to build and maintain their structures. The fossil record shows a catastrophic decline in calcifying organisms at the KPG boundary. Ammonites, which had survived for over 7 million years and multiple previous extinction events, disappeared completely. Certain groups of planktonic foraminifera, microscopic shelled protists, suffered near total extinction, with only a handful of species surviving. Calcareous nanoplankton, microscopic algae with calcium carbonate scales, also suffered severe losses. These organisms were crucial primary producers in marine ecosystems. Their decline would have devastated marine food webs. The ocean took tens of thousands to hundreds of thousands of years to recover its carbonate chemistry, to rebuild populations of calcifying organisms, to reestablish the marine ecosystems that had existed before the impact. Toxic atmosphere. The impact and its aftermath created atmospheric conditions far outside the range that life had evolved to tolerate. The vaporization of sulfur-rich rocks created sulfuric acid rain. Nitrogen oxides formed from the heat of impact and from wildfires. The chemistry of the atmosphere became hostile. Acid rain would have further damaged vegetation, acidified freshwater environments. leached nutrients from soils. Combined with the darkness, the cold, and the loss of primary production, it contributed to the cascading collapse of ecosystems. Longer-term effects, even after the initial impact winter faded, after dust settled, after temperatures began to recover, the planet was changed. Vegetation patterns were altered, species compositions shifted, ecosystems had to rebuild from the survivors, and the survivors were not a random sample of what had existed before. The impact also triggered or intensified volcanic activity. The Deccan Traps, massive flood basalts in what is now India, were already erupting before the impact, but evidence suggests the eruption rate increased dramatically after the impact. Some scientists think the seismic shock of the impact, traveling through the planet, may have fractured magma chambers, increasing volcanic output. These eruptions released additional II and sulfur dioxide, prolonging atmospheric disruption, complicating recovery. For hundreds of thousands of years after the impact, Earth's climate was unstable, oscillating between cold periods from volcanic sulfur and warm periods from CO2 buildup. This prolonged instability made recovery difficult. Species that survived the immediate aftermath still faced a world that was unpredictable, hostile, unlike anything they had evolved to cope with. Extinction is never total. Even the worst mass extinctions in Earth's history leave survivors. The KPG extinction was no exception. Understanding what survived and why tells us a lot about the killing mechanisms and about the nature of extinction itself. The survivors, birds survived. Not all birds. Many lineages went extinct, but representatives of several groups made it through. These were mostly small-bodied species, likely omnivorous or able to survive on seeds and detritus. Birds that nested in burrows or in protected locations, that could enter torpor to conserve energy, that could survive on limited food for extended periods, these had advantages. Modern birds, all Surling species, descend from these KPG survivors. The extinction wiped out most bird lineages, but the survivors radiated in the Paleogene, diversifying to fill niches left vacant by extinct dinosaurs and pterosaurs. Mammals survived. Again, not all mammals. Some lineages disappeared. But multiple groups made it through. These were mostly small. The largest was perhaps Serfu kilograms, about the size of a raccoon. They were likely omnivorous, burrowing, nocturnal. After the extinction, mammals radiated explosively. Within million years, they had diversified from mouse-sized insectivores to animals weighing several tons. The extinction of non-avian dinosaurs removed competitive pressure and predation pressure, allowing mammals to exploit niches that had been unavailable during the Mesozoic. Crocodilians and their relatives survived. These are large ectotherms, cold-blooded animals. So why did they survive when non-avian dinosaurs didn't? Several factors. Crocodilians are semi-aquatic, spending time in water that provided protection from heat and cold. They can survive long periods without food by entering a state of dormancy. They're scavengers and opportunistic feeders, able to eat a variety of food sources. And they have slower metabolisms than endotherms, requiring less energy. Turtles survive. Similar reasoning applies. Many are aquatic or semi-aquatic. They can enter torpor. They have low metabolic requirements. They can survive on limited food. Amphibians survived, though they also suffered losses. Their aquatic larvae and ability to shelter in moist environments probably helped. Many amphibians can also enter dormancy during unfavorable conditions. Fish survived. Freshwater fish had higher survival rates than marine fish, possibly because freshwater environments were less affected by ocean acidification, or because freshwater ecosystems are more localized and some refugia escaped the worst effects. Sharks survived. Despite being marine predators, sharks made it through, though some groups went extinct. Their diversity today stems from post-extinction radiation. Insects survived. Their small size, short generation times, ability to enter diapause dormancy, and feeding on detritus or dead material probably contributed. Pollinators like bees may have survived on stored pollen or switched to feeding on wind-pollinated plants or detritus. Plants survived, but with major changes in composition. Ferns, which reproduce by spores rather than seeds and can colonize disturbed environments quickly, show a fern spike in the fossil record immediately after the KPG boundary, a brief period where fern spores dominate the pollen and spore record, suggesting widespread die-off of seed plants followed by fern colonization. Flowering plants as a group survived and thrived. Many individual species went extinct, but the group as a whole recovered quickly. Conifers and other gymnosperms also survived. Though some lineages disappeared. Seeds, particularly those capable of remaining dormant in soil for years, provided a survival mechanism. When light returned and conditions improved, these seeds could germinate, recolonizing devastated landscapes. The pattern of survival reveals something crucial about extinction events. Success during normal times doesn't guarantee survival during catastrophes. The dinosaurs were supremely adapted to the Cretaceous world. They had evolved over million years to thrive in those conditions, but that specialization became a vulnerability when conditions changed rapidly and drastically. Size matters. One of the clearest patterns in the KPG extinction is size selectivity. Large-bodied animals suffered disproportionately. In the terrestrial realm, no land animal larger than about 12 kilograms survived unless it was semi-aquatic, like crocodilians. Why? Large animals require more food. They have higher absolute energy requirements even if their mass-specific metabolic rates are lower. During a collapse in primary production, food becomes scarce. A mouse can survive on seeds and insects. An elephant cannot. Large animals also have longer generation times, slower reproductive rates, smaller population sizes. They're less able to adapt quickly to changing conditions through natural selection. They can't hide in burrows or sheltered microhabitats. They can't migrate easily if their habitat is destroyed. The extinction was not kind to specialists or to apex predators. Tyrannosaurus rex, the ultimate specialist carnivore, required enormous amounts of meat. When herbivore populations crashed, Rex had nothing to eat. Similar logic applies to large herbivores. They needed vast quantities of vegetation that simply wasn't available during the impact winter. The geography of survival, location mattered. Organisms in certain environments had higher survival probabilities than others. Freshwater environments served as refugia. Lakes, rivers, and swamps provided buffering against temperature extremes, protection from the heat pulse, food sources in the form of detritus and aquatic vegetation. Animals that could exploit these environments, amphibians, turtles, crocodilians, freshwater fish, had advantages. Coastal marine environments suffered more than deep ocean environments. The impact may have generated tsunamis hundreds of meters tall that scoured coastlines. The heat pulse would have affected shallow water more than deep water. Ocean acidification would have been more severe at the surface than at depth. High latitudes may have provided some advantages. These regions were already adapted to seasonal darkness, the polar winter. Ecosystems there may have been more resilient to prolonged darkness than tropical ecosystems that experienced consistent sunlight year-round. However, the cold of the impact winter would have been severe at high latitudes, so this advantage is debated. Soil communities, the complex assemblages of bacteria, fungi, invertebrates, and microorganisms that live in Earth, largely survived. These communities are crucial for decomposition, nutrient cycling, and ultimately for ecosystem recovery. Their survival meant that when light and warmth returned, the basic infrastructure for rebuilding ecosystems remained intact. You might be wondering, how can scientists reconstruct a single-day Loser Loop million years ago in such detail? How do we know an asteroid hit Earth? How do we know where it struck, how big it was, what effects it had? The evidence is written in rock, in chemistry, in the distribution of fossils, in shocked minerals and impact spherules, in the geometry of the crater itself. Let me take you through the detective story that is modern impact, geology, and extinction science. In the iridium anomaly, the first crucial evidence came in, Ichenjo by Bashers, when physicist Luis Alvarez, his geologist son Walter Alvarez, and their colleagues published a paper in the journal Science. They had been studying a thin clay layer at the Cretaceous-Paleogene boundary in Gubbio, Italy. This boundary layer is visible in rock formations worldwide, a distinct marker where the fossils of the Cretaceous abruptly disappear and are replaced by different organisms of the Paleogene. It's the physical manifestation of the extinction event, preserved in stone. The Alvarezes measured the chemical composition of this boundary clay and found something extraordinary. It was enriched in iridium by a factor of sensors compared to the rocks above and below it. Iridium is a platinum group element, rare in Earth's crust because it tends to sink into the core during planetary differentiation. It's common in asteroids, which never underwent this differentiation. The iridium enrichment suggested that extraterrestrial material had been deposited globally at the KPG boundary. The amount of iridium spread across the entire planet implied an asteroid roughly kilometers in diameter, exactly the size estimated from other evidence. Since Ichenjo by Bashers, the iridium anomaly has been confirmed at hundreds of KPG boundary sites worldwide. It's a global marker, a fingerprint of the impact. Shocked quartz. When rocks experience pressures above about gigapascals, pressures far higher than anything achievable through normal geological processes like tectonic collisions or volcanic eruptions, the crystal structure of quartz grains undergoes permanent deformation. The crystals develop planar deformation features, parallel lines visible under a microscope. This shocked quartz is diagnostic of impact events or nuclear explosions. It's found at nuclear test sites and meteorite impact craters, and it's found globally in the KPG boundary layer. The shocked quartz at the boundary shows multiple sets of planar features indicating pressures of Erders-Fusser gigapascals or higher. This level of shock can only be produced by an asteroid impact, not by volcanoes or any other terrestrial process. So, the shocked quartz provides independent confirmation of the impact hypothesis and allows scientists to estimate the intensity of the shock wave that radiated from the impact site. Tektites and impact spherules in North America and the Caribbean. The KPG boundary contains layers of small glass spherules, millimeter-sized beads of once molten rock that cooled rapidly. These are impact spherules, formed when molten rock ejected by the impact was thrown into the atmosphere, formed into droplets, and solidified during flight. Some sites contain layers of these spherules meters thick, particularly in regions closer to the impact point. The spherules contain shocked minerals. They're chemically distinct from volcanic glass, and their distribution points back to a source in the Caribbean region. Tektites, larger pieces of impact glass, are found in Haiti and other locations. These glassy objects formed from rock melted by the impact, ejected at high velocity, and cooled in flight. Their aerodynamic shapes and chemical compositions are consistent with impact origin. The crater, For years after the Alvarez hypothesis was published, scientists searched for the impact crater. A crater from a kilometer asteroid should be fu kilometers in diameter. One of the largest on Earth. But where was it in Ichanjobjolsur? The crater was definitively identified. It was hiding beneath the Yucatan Peninsula in Mexico, buried under hundreds of meters of younger sediment. The crater, named Chicxulub after a nearby town, is about Bashers kilometers in diameter, precisely matching predictions. The crater had actually been discovered decades earlier by petroleum geologists using magnetic and gravitational surveys, but they hadn't recognized it as an impact structure. Its significance was only understood after the Alvarez hypothesis focused attention on finding a KPG boundary crater. Drilling into the crater has recovered impact melt rock, granite basement melted by the shock of impact and cooled rapidly to form glass. This melt rock contains shocked minerals, high-pressure polymorphs of quartz and other minerals, and chemical signatures of both the target rock and the asteroid. The crater structure itself reveals details of the impact. The presence of a peak ring indicates a complex crater formed by a large energetic impact. The distribution of ejecta around the crater matches computer models of oblique impacts at approximately Richter's degrees from horizontal. And dating of the impact, melt, and boundary layer sediments gives an age of Luxor-Ludartling million years ago, with uncertainty of only about Shilling years. Remarkable precision for an event so ancient. The fossil record, ultimately the most compelling evidence, comes from fossils. The pattern of extinction is sharp and dramatic. In the Hell Creek Formation of Montana and the Dakotas, one of the best-studied KPG boundary sections, dinosaur fossils are abundant in Cretaceous rocks right up to the boundary layer. Above the boundary, they disappear completely and permanently. No non-avian dinosaur fossils have ever been found in rocks definitively younger than the KPG boundary. The same pattern holds for ammonites, for pterosaurs, for many groups of marine reptiles, for certain groups of plankton. The extinction is geologically instantaneous, happening in a time frame too short to resolve with dating techniques. This sharp extinction rules out gradual decline scenarios. The organisms didn't slowly die out over millions of years. They were thriving right up until the impact, and then they were gone. Impact proxies and climate indicators, geochemical analyses of boundary layer sediments reveal the environmental effects of the impact. Soot layers indicate global wildfires. Sulfur isotope ratios indicate massive injection of sulfate into the atmosphere. Carbon isotope excursions indicate disruption of the carbon cycle and collapse of primary production. Fossil charcoal, wood burned and preserved as carbon, is common in boundary layer sediments, providing direct evidence of wildfires. The ratio of charcoal to unburned organic matter suggests that a significant fraction of global biomass burned. Temperature proxies, oxygen isotope ratios in fossil shells, organic geochemistry indicators show evidence of rapid cooling following the impact, consistent with impact when the evidence is overwhelming, coming from multiple independent lines of inquiry, all pointing to the same conclusion. Million years ago, an asteroid roughly kilometers in diameter struck Earth in what is now the Yucatan Peninsula, releasing energy equivalent to million megatons of TNT, triggering global environmental catastrophe and causing the extinction of approximately 500 Chisarwur of species on Earth. The impact winter eventually ended, dust settled, sulfur aerosols rained out, temperatures began to recover, sunlight returned to Earth's surface, and life, persistent and opportunistic, began to rebuild. But the world that emerged from the darkness was fundamentally different from the one that had existed before. The recovery was not a return to pre-impact conditions. It was the birth of a new world, our world, the Cenozoic era. The first survivors, the disaster flora, when light levels recovered sufficiently for photosynthesis, the first plants to recolonize were pioneer species, ferns primarily. The fern spike visible in the fossil record represents a brief period, perhaps thousands of years, when ferns dominated terrestrial ecosystems. Ferns reproduce via spores, which are small, numerous, and can disperse widely. They can colonize disturbed ground quickly. In the devastated post-impact landscape, with soils exposed, dead biomass abundant, and competition minimal, ferns thrived. But they were soon followed by flowering plants, seeds that had survived in the soil. Seeds that had been transported by survivors began to germinate. Within tens of thousands of years, forests were regrowing, though their composition was different from before. Some plant lineages had gone extinct, others had survived in isolated refugia and began to spread. New ecological relationships formed. The world of the early Paleogene was a time of ecological experimentation, of communities assembling in novel configurations. Flowering plants, angiosperms, became even more dominant than they had been in the Cretaceous. They diversified rapidly, evolving new forms, new ecological strategies, new relationships with pollinators and seed dispersers. The modern dominance of flowering plants, which make up about 500 koshas of terrestrial plant species today, was established in the aftermath of the KPG extinction, the rise of the mammals. For about 1 million years, mammals had lived in the shadow of dinosaurs. They were mostly small, mostly nocturnal, occupying ecological niches that didn't compete directly with dinosaurs. The largest Mesozoic mammals were badger-sized. Most were much smaller. The extinction of non-avian dinosaurs changed everything. Suddenly, ecological niches were vacant, herbivore niches, from small browsers to large grazers, carnivore niches, from small insectivores to apex predators, arboreal niches, aquatic niches. All were available. Mammals radiated into this empty ecospace with extraordinary speed. Within million years of the extinction, a geological eye blink, mammals had diversified from shrew-sized insectivores to animals weighing several tons. The first large herbivorous mammals appeared within 10 million years of the impact. These early giants, like the pantodont Berylambda, were still relatively primitive, with sprawling postures and less efficient locomotion than later mammals. But they were large, weighing hundreds of kilograms, exploiting vegetation niches that no mammal had accessed during the Mesozoic. Carnivorous mammals also diversified. Early Paleogene carnivores included creodonts and early members of the carnivore lineage. By million years after the impact, there were mammalian apex predators filling roles similar to those of theropod dinosaurs in the Cretaceous. The radiation wasn't just about size. Mammals evolved diverse adaptations, specialized teeth for different diets, cursorial running adaptations for pursuit, predation, or escape, arboreal adaptations for life in trees, aquatic adaptations for life in water. They evolved complex social behaviors, sophisticated sensory systems, large brains capable of learning and flexible behavior. By the Eocene, million years after the extinction, the modern mammal orders were established. Primates, rodents, ungulates, hoofed mammals, cetaceans, whales, bats, carnivores, all had evolved and were diversifying. The age of mammals had begun, the avian radiation. Birds, too, radiated in the post-extinction world. The survivors of the KPG event were relatively few lineages, likely small-bodied omnivores or seed-eaters. But from these survivors came the extraordinary diversity of modern birds. Within several million years, most modern bird orders had appeared. Water birds, ducks, shore birds, flamingos, land birds, pigeons, parrots, woodpeckers, songbirds, predatory birds, hawks, owls, large flightless birds, which in the early Cenozoic filled some of the niches left vacant by non-avian dinosaurs. Yet one remarkable group deserves mention, the forest racids, or terror birds. These were large, flightless predatory birds that evolved in South America and reached heights of centimeters and weights of kilograms or more. They had massive hooked beaks, powerful legs, and were apex predators in their ecosystems for millions of years. Terror birds represent a fascinating case of evolutionary convergence, birds re-evolving. The predatory role their theropod dinosaur ancestors had played in the Mesozoic, Sosic. They were successful for tens of millions of years until competition with mammalian carnivores and climate change led to their extinction. Marine recovery in the oceans was slower than on land. The collapse of photosynthesis, the ocean acidification, and the extinction of key plankton groups disrupted marine food webs fundamentally. And plankton communities took hundreds of thousands to millions of years to recover. New species evolved to fill niches left by extinct lineages. The ecosystem structure of the ocean changed. Different plankton species dominated, leading to different food web dynamics. Ammonites never recovered. Despite surviving for over 7 million years and multiple previous mass extinctions, they went completely extinct at the KPG boundary. Their ecological role, mid-level predators and prey in marine food webs, was taken over by other cephalopods, fish, and eventually marine mammals. Marine reptiles like mosasaurs and plesiosaurs also disappeared. Their niches were eventually filled by sharks which had survived and by new groups of marine mammals, whales, dolphins, pinnipeds, seals, and sea lions that evolved from terrestrial ancestors and returned to the sea during the Cenozoic. Coral reefs, which had been devastated by the extinction, took millions of years to recover. The reef systems of the early Paleogene were different from those of the late Cretaceous, built by different organisms with different ecological structures, long-term climate effects. The Earth's climate in the aftermath of the impact was unstable for hundreds of thousands of years. The initial impact winter gave way to warming as CO2 from the impact and from the Deccan Traps volcanic eruptions accumulated in the atmosphere. The early Paleocene, the first epoch of the Paleogene period, was characterized by generally warm conditions, but with significant fluctuations. One notable event, the Paleocene-Eocene thermal maximum about million years ago, saw global temperatures spike by degrees Celsius over a few thousand years, possibly triggered by massive release of methane from ocean sediments. These climate fluctuations affected the recovery and evolution of ecosystems. Some lineages thrived in warm periods, others in cooler intervals. The climate instability may have driven evolutionary innovation as species adapted to changing conditions. And gradually, over millions of years, the climate stabilized. The scars of the impact faded. New ecosystems, new communities, new evolutionary trajectories became established. The Cretaceous world was gone, replaced by something new. While the asteroid impact hypothesis is now widely accepted, the story is more complex than asteroid hits. Dinosaurs die. There's ongoing scientific debate about the relative importance of different factors and about whether the impact was the sole cause or merely the final blow to ecosystems already under stress. And the Deccan Traps controversy. The Deccan Traps are one of the largest volcanic features on Earth. Flood basalts covering over square kilometers in what is now India. These weren't normal volcanic eruptions. They were massive outpourings of lava from fissures in the crust, eruptions that lasted for hundreds of thousands of years. The Deccan Traps eruptions began before the KPG boundary, perhaps 1 million years before, and continued after it. The timing is provocative. Could these eruptions have caused the extinction instead of or in addition to the asteroid impact? And volcanic eruptions release CO2, causing warming. They also release sulfur dioxide, causing cooling and acid rain. The environmental effects of the Deccan eruptions would have been significant, though operating on longer timescales than the asteroid impact. Some scientists argue that the Deccan eruptions weakened ecosystems, making them more vulnerable to the asteroid impact. In this view, the extinction required both the sustained stress from volcanism and the acute shock from the impact. Others argue that the asteroid impact triggered increased Deccan volcanism by sending seismic waves through the planet that fractured magma chambers, increasing eruption rates. There's some evidence for increased eruption tempo immediately after the impact, though this is debated. The current scientific consensus is that the asteroid impact was the primary cause of the extinction, but that the Deccan eruptions likely contributed to environmental stress and may have influenced the severity and recovery patterns of the extinction. Gradualism versus catastrophism. Before the impact hypothesis was established, some paleontologists argued that dinosaurs were already in decline before the KPG boundary, suffering from long-term environmental changes. Competition with mammals. This gradualist view has largely been abandoned. The fossil record shows dinosaurs thriving right up to the boundary. Diversity wasn't declining in the latest Cretaceous. New species were still evolving. There's no evidence of long-term decline. However, some researchers note regional variations. Dinosaur diversity in North America may have been slightly lower in the very latest Cretaceous than earlier. Though this could be sampling bias, fewer rocks of that age have been studied. The debate highlights an important point. Mass extinctions have causes operating on different timescales. Background stresses, climate change, sea level fluctuations, volcanic activity may set the stage, but the extinction itself is triggered by a catastrophic event. In this case, the asteroid impact, selectivity patterns, and killing mechanisms. Understanding why some lineages went extinct while close relatives survived remains an active area of research. Why did non-avian dinosaurs die out while birds survived? Why did ammonites disappear while nautilus, their shelled cephalopod relatives, survived? The answers likely involve complex interactions between physiology, ecology, geography, and luck. Birds that could shelter, that had low food requirements, that could enter torpor, these survived. Ammonites that lived in surface waters, that were affected by acidification, that couldn't find food during the collapse of marine primary production, these perished. Nautilus, in contrast, lives in deeper water, has lower metabolic requirements, can survive long periods without food. These traits may have been crucial for survival. Similarly, freshwater turtles survived while many marine turtles went extinct. Crocodilians survived while many terrestrial archosaurs didn't. The pattern suggests that freshwater environments served as refugia, buffering against the most extreme effects of the impact. The role of chance. Finally, it's important to acknowledge the role of random chance. Not every extinction is perfectly explainable by adaptive differences. Sometimes populations go extinct because they happen to be in the wrong place, or because their population size was too small to survive a bottleneck, or because the specific refugia they depended on were destroyed. The fossil record shows that many surviving lineages went through severe population bottlenecks at the KPPG boundary. They survived, but just barely. If a few more individuals had died, if a few more populations had been wiped out, those lineages might have joined the dinosaurs in extinction. Evolution is not directional or purposeful. Survival is not always about being the fittest in normal times. During catastrophes, survival can depend on traits that are neutral or even disadvantageous under normal conditions. The ability to hibernate, to eat unusual foods, to survive in marginal habitats. The extinction reminds us that life's history is contingent, dependent on events that can't be predicted or controlled, shaped by catastrophes that reset the rules and create opportunities for survivors. Why does this ancient catastrophe matter today? Why should we care about events low million years in the past? Because the threat hasn't gone away. Asteroids still exist. Orbits still evolve. Impacts still happen. And the ongoing threat, Earth, exists in a cosmic shooting gallery. The solar system contains millions of asteroids, ranging from pebble-sized to mountain-sized and larger. Most orbit in the asteroid belt between Mars and Jupiter, but some have orbits that bring them into the inner solar system, crossing Earth's orbit. And these near-Earth asteroids, NEAs, are the ones we worry about. They're approximately lean known NEAs larger than e-byte sismimeters in diameter, large enough to cause significant regional damage. About E-Ling NEAs are larger than E-kilometer, large enough to cause global effects if they struck Earth. And we've cataloged most of the kilometer-sized NEAs. None of them pose an imminent threat, but smaller asteroids, hundreds of meters in diameter, are harder to detect, and we haven't found all of them. An impact from a Urbach-meter asteroid wouldn't cause mass extinction, but it could devastate a city or trigger massive tsunamis if it struck an ocean. Tops. The probability of a civilization-threatening impact from an asteroid, e-kilometer or larger, in any given century is low, perhaps bifunded Ling E2, bifunded Ling E, but over long time scales, it's not a question of if, but when. Detection and deflection. The good news is that we're not as helpless as the dinosaurs. We can detect asteroids. We can track their orbits, and we're developing the capability to deflect them. NASA's Planetary Defense Coordination Office monitors NEAs, calculating their orbits decades or centuries into the future, identifying ground-based telescopes and space-based observatories like NEWIS search for previously unknown asteroids. In Arsene Arserar, NASA successfully tested asteroid deflection technology with the DART Double Asteroid Redirection Test mission. A spacecraft deliberately crashed into the small asteroid Dimorphos, changing its orbit slightly. The test proved that kinetic impactors, essentially high-speed spacecraft crashes, can alter asteroid trajectories. For asteroids detected decades in advance, even small changes in velocity can shift their orbit enough to miss Earth. A deflection of a few centimeters per second, applied years before a potential impact, can move the asteroid's position by thousands of kilometers by the time it would have reached Earth. Other deflection methods are being studied, gravity tractors, spacecraft using their own gravity to slowly pull asteroids off course. Nuclear devices not to destroy the asteroid, which would create multiple dangerous fragments, but to vaporize material from one side, creating thrust, laser ablation, mass drivers, and more. The key is early detection. With years or decades of warning, deflection is feasible. Without warning, we're back in the dinosaur's position, helpless to prevent catastrophe. Lessons for existential risk. The KPG extinction teaches us about existential risks, low probability, high consequence events that threaten civilization or humanity itself. First lesson, dominance is not immunity. The dinosaurs were the most successful land animals ever, having thrived for million years. Yet a single event ended them. Success in normal times doesn't protect against catastrophes that change the rules. Second lesson, complex systems are vulnerable to cascading failures. The impact didn't kill everything directly. It triggered a cascade, fires, impact winter, ecosystem collapse, where each effect amplified others. Modern civilization, with its interconnected systems, global supply chains, and dependencies on stable climate and ecosystems, may be similarly vulnerable to cascading failures from various triggers. For third lesson, recovery takes time. Even after the immediate catastrophe ended, ecosystems took millions of years to fully recover. Civilization might not have millions of years. We need to prevent catastrophes, not just survive and recover from them. Fourth lesson, small things matter. The survivors weren't the most powerful or dominant organisms. They were the small, the flexible, the ones who could shelter and scavenge and endure. In human terms, resilience, the ability to maintain function during disruptions, may be more important than optimization for current conditions. Climate change parallels. The KPG extinction provides a case study in rapid environmental change and its effects on ecosystems. While climate change today operates on longer timescales than an asteroid impact, decades to centuries rather than days, the lessons remain relevant. The impact disrupted the carbon cycle, changed the atmosphere's composition, altered temperature and precipitation patterns, acidified the oceans. Modern climate change does the same things, though through different mechanisms. Burning fossil fuels instead of vaporizing limestone, releasing CO2 over centuries instead of days. The biological responses show what happens when environmental change outpaces adaptation, range shifts, species extinctions, ecosystem restructuring. Large specialists suffer most. Small generalists do better. Recovery takes far longer than the disruption. We're conducting an experiment on Earth systems, changing atmospheric composition faster than at any time in the past. Looser loop million years, except the immediate aftermath of the impact. The KPG extinction shows us that Earth systems can absorb enormous perturbations and eventually recover, but not necessarily in forms we would recognize or find hospitable. The deep time perspective, perhaps the most profound lesson from the KPG extinction, is about timescales and perspective. 66 million years is incomprehensible to us. Our entire species, Homo sapiens, has existed for only ling years. Civilization is ling years old. Written history is Wuling years. A human lifetime is less than Ebat years. From our perspective, the Cretaceous is ancient, the extinction unimaginably remote. But Earth remembers. The iridium layer still exists, globally distributed. The crater is still there, preserved beneath younger sediments. The evolutionary consequences, the absence of non-avian dinosaurs, the dominance of mammals and birds, shape the world we inhabit. We are the asteroid's children, in a sense. Mammals only became dominant because the impact removed the dinosaurs. Primates evolved in the trees of Paleocene forests that grew in the aftermath of extinction. Humans exist because of a cosmic accident, Loxer Loop million years ago. This deep time perspective is humbling. Species rise and fall, ecosystems form and collapse, continents move, climates change. Life persists, but not necessarily in the forms that existed before. Our tenure on Earth is brief. So far, a geological instant. Whether we become a long-lived species, persisting for millions of years, or whether we're a flash in the pan, depends partly on how well we understand the lessons of deep time, how seriously we take low-probability catastrophic risks, how wisely we manage our relationship with the planet and with the universe beyond. The story of the KPG extinction is not complete. New discoveries continue to reshape our understanding, answering old questions and raising new ones. Recent discoveries in Arsending Isherliu, scientists drilling into the Chicxulub crater recovered core samples from the peak ring, the circular mountain of shocked and melted rock that formed during crater rebound. These cores provided unprecedented detail about impact processes, revealing the speed of peak ring formation, the nature of impact melting, and the immediate post-impact environment. One surprising finding, life returned to the crater remarkably quickly. Within years to decades, the hot, sterile impact site was colonized by microorganisms. Within thousands of years, more complex ecosystems had established themselves. The crater itself became a refugium, a place where life recovered and diversified. Researchers announced the discovery of a fossil site in North Dakota, preserving animals killed within hours of the impact over San Ling kilometers from Chicxulub. The site, called Tanis, contains fish with impact spherules in their gills, suggesting they died while the spherules were falling. Mixing of marine and freshwater organisms suggesting tsunami-like flooding, and other evidence of catastrophic, sudden deposition. While some aspects of the Tanis site remain controversial and are being debated in the scientific literature, if confirmed, it provides a remarkable snapshot of the day of the impact, the only known site preserving the immediate aftermath. Advances in geochemistry have allowed more detailed reconstruction of post-impact climate. Studies of fossil leaves, of isotopes in marine sediments, of molecular fossils, organic compounds preserved in rocks are revealing the temperature fluctuations, the duration of the impact winter, the timing of recovery. Computer modeling has advanced enormously. Modern simulations can track the asteroid from entry through impact, through crater formation, through atmospheric injection of ejecta, through global dispersal of material. These models are being constantly refined as new data emerges and computational power increases. Unanswered questions. Despite decades of research, significant questions remain. How long did the impact winter last? Estimates range from months to years to over a decade. Different climate models, different assumptions about atmospheric particle loading, different interpretations of geochemical proxies give different answers. The duration matters for understanding which organisms could survive and how long food chains could sustain themselves without photosynthesis. What was the geographic pattern of survival? Did certain regions serve as refugia, where extinction was less severe? Were there areas where ecosystems collapsed completely versus areas where communities remained partially intact? The fossil record is incomplete, biased towards certain environments and regions, making global patterns hard to discern. How important were the Deccan traps? Did they precondition ecosystems for collapse, making the impact more devastating than it would otherwise have been? Or were they a separate stressor that happened to coincide? Better dating of the eruptions, better understanding of their atmospheric effects, and better integration of volcanic and impact scenarios are needed. Why did some specific lineages survive while others didn't? Why did modern bird lineages survive, while enantiornithines, a diverse group of Mesozoic birds, went extinct? Why did some groups of plankton disappear, while close relatives survived? The details of selectivity patterns hold clues to killing mechanisms, but remain incompletely understood. Expanding the context, other mass extinctions. The KPG extinction is the most famous, but it's not the largest mass extinction in Earth's history. That distinction belongs to the end Permian extinction, Arbek-Wushurar million years ago, which killed approximately baffinid cultures of marine species and baffinid tissures of terrestrial vertebrate species. The end Permian extinction was not caused by an asteroid. It resulted from massive volcanic eruptions in Siberia, climate change, ocean acidification, ocean anoxia, oxygen depletion, and possibly other factors acting together over hundreds of thousands of years. The recovery took millions of years. Comparing mass extinctions reveals common patterns: disruption of the carbon cycle, rapid environmental change, ecosystem collapse, selective extinction, favoring small generalists over large specialists, long recovery times. But the specific mechanisms differ. Not all mass extinctions involve impacts. The end Permian, the late Devonian extinctions, the end Triassic extinction, all seem to have been caused primarily by volcanism, climate change, or ocean chemistry changes rather than extraterrestrial impacts. However, impacts have happened multiple times. The Chesapeake Bay crater on the U.S. East Coast, the Popigai crater in Russia, the Manicouagan crater in Canada, all record significant impacts, though none as large as Chicxulub. Some extinction events may have involved multiple impacts. Understanding the variety of extinction mechanisms, the interactions between different stressors, the factors that make some extinctions more severe than others, this comparative approach enriches our understanding of each individual event. The Anthropocene question. We live in the Anthropocene, an informal term for the current geological epoch characterized by significant human impact on Earth's geology and ecosystems. Some scientists argue we're causing the sixth mass extinction, rivaling the big five mass extinctions of the Phanerozoic. Current extinction rates are EBET2E, ling times higher than background rates. Species are disappearing due to habitat destruction, climate change, pollution, overexploitation, and invasive species. Ecosystems are being transformed globally. However, the comparison to previous mass extinctions is debated. We haven't yet reached the Babylonichisser species loss threshold of the KPG extinction. The timescale is different. Current extinctions are happening over centuries, not days. The mechanisms are different. No asteroid, no global firestorm, no impact winter. But the trajectory is concerning. If current trends continue for centuries, the cumulative species loss could indeed rival past mass extinctions. Unlike the dinosaurs, we can see the catastrophe coming. Unlike the dinosaurs, we can change course. The KPG extinction reminds us that mass extinctions happen, that dominant groups can disappear, that recovery takes geological timescales. It provides both warning and hope. Warning that life on Earth is vulnerable to catastrophic change. Hope that even the worst catastrophes don't extinguish life entirely, that evolution.
We return to where we began.
Standing in the present, looking back through deep time to a single day, Loserloop million years ago. The asteroid that struck Earth that day changed everything. Not just for the dinosaurs, though their extinction is the most visible legacy, but for the entire trajectory of life on Earth. Without the impact, mammals might have remained small, nocturnal, marginal. Dinosaurs might have continued their reign for millions more years. Birds might not have diversified into species. The ecosystems we know, the animals we're familiar with, the very world we inhabit, none of it would exist in its current form. We exist because of catastrophe. Our ancestors, small frightened mammals hiding in burrows while the world burned, survived because they were small enough to shelter, flexible enough to eat anything, hardy enough to endure months of darkness and cold. They survived while the mighty perished. That's a humbling lesson. Power, dominance, specialization. These are advantages in stable times. But when the world changes suddenly and drastically, survival favors the flexible, the small, the hidden. The meek, as an ancient text says, inherit the earth, but inheritance, comes with responsibility. We've inherited a planet still recovering from that ancient catastrophe, still bearing its scars, still shaped by its consequences. We've inherited a universe that contains asteroids, a solar system filled with debris, a cosmos indifferent to our survival. We're the first species capable of understanding this history, capable of reading the story written in shocked quartz and iridium anomalies and fossilized bones. We're the first species capable of detecting asteroids before they strike, capable of potentially deflecting them. We're the first species capable of causing environmental changes on a scale comparable to an asteroid impact, though through different mechanisms. This knowledge is power, but also burden. We know what happened to the dinosaurs. We know that dominant species can disappear. We know that ecosystems can collapse. We know that recovery is slow. Claim ignorance. The question facing humanity in the early 16th century is whether we'll use this knowledge wisely. Will we monitor the skies for threats and develop the technology to prevent them? Will we manage our relationship with Earth systems sustainably, avoiding the catastrophic disruptions that trigger extinction events? Will we build resilience into our civilization, ensuring that if disasters do occur, some of us survive to carry forward the light of consciousness and culture? Or will we, like the dinosaurs, be caught unprepared by catastrophe? Will future paleontologists, if any exist, study our fossil layer and wonder what we did wrong, why we couldn't adapt, why such an intelligent species nonetheless failed to ensure its survival? Now, these questions have no certain answers. History is contingent, the future is unwritten. Asteroids still hurtle through space, their orbits chaotic, their future positions uncertain. Climate still changes. Ecosystems still face stressors. Extinction is still possible, but unlike the dinosaurs, we can imagine the future. We can learn from the past. We can take action to improve our odds. We can't eliminate risk. That's impossible in a universe governed by probability and chance. But we can reduce it, prepare for it, build systems that are resilient to it. And the Chicxulub asteroid was roughly 6 kilometers wide. It traveled Rs kilometers per second. It released about million megatons of energy. It killed 500 chisor of species on Earth. It ended the age of dinosaurs and began the age of mammals, and it reminds us every time we look at the night sky that space is not empty, that time is vast, that life is precious, that survival is never guaranteed, and that the universe, beautiful and terrible, contains wonders and horrors beyond our imagination. Okay. The dinosaurs had Ebite-Losherwu million years. We've had Sembite-Ling years as a species, Sarling years of civilization. How long will we last? That depends on choices we make now, on how seriously we take the lessons of deep time, on whether we can muster the wisdom to match our technological power. The asteroid is out there, somewhere, maybe not one with our name on it, not in our lifetimes, but eventually, inevitably, unless we're prepared, unless we're vigilant, unless we're lucky, the clock is always ticking. The universe is always dangerous, and life, persistent and adaptable, continues its ancient dance with extinction. This has been the story of the day the world changed forever. Thank you for taking this journey through deep time with me. If you found value in this exploration, I encourage you to learn more, to look at the rocks beneath your feet with new eyes, to understand that you're standing on a planet with memory, with history written in stone and ash, and the bones of creatures that once ruled and are no more. You can remember the dinosaurs, remember the asteroid, remember that we're all children of catastrophe, descendants of the survivors, inheritors of a world remade by cosmic violence. And remember that the story isn't over. We're still writing it day by day, choice by choice, building toward whatever future awaits. The asteroid has fallen. Answering, the dust has settled. Life goes on for now,